Welcome to the computer science series. As a part of this series, this is a course on artificial intelligence, and in this course we are recapping the unit 2. Last few classes we have been doing search techniques, and the first part of this lecture will be a recap of the entire search techniques, and then I will move on to unit 3. So, basically we started off with how to represent a problem through search. In AI, this is the fundamental part. For a given problem, it can be represented into 5 terms. The first one is the states, where it consists of S0 to Sn, and if you see in the right hand side, we have the state S0, we apply some, it goes to S1, and this is the end point, which is the goal. The initial state, it is S0, the final state is Sn, successor function otherwise called as an action, where once we have the starting point, we apply some action or the successor function, it moves to the next state and so on. So, the entire search that we did in unit 2, we are going to represent in terms of these 5 values, and the last one is the cost. This is the numeric value. If it is not given, we will just assume this is an identity or the unit cost. Now, with this representation, we did 2 types of searches. One, it was uninformed search, and the second one is informed search. In the uninformed search, we started off with some S0 and moved just randomly, we picked a point, moved until we reached to the goal. And at this point of the search techniques, we did all these techniques, where the first one is breadth first search, the second is depth first, the third is uniform cost search, fourth is depth limited, and fifth is iterative deepening. All these again the essence is, first we start with some kind of the state and we apply an action, a random action to it, and then we move until we reach the goal, or in other words, the information of goal is not known. Whereas, in the informed search, we have some kind of heuristic. Suppose we start at some point, okay, if the goal is here, then we would have some kind of heuristics. One example is the triangular inequality, where we did in the map of Romania. So, from the heuristics point of view, there are some algorithms like greedy A star algorithm, and we also did some optimal search techniques like hill climbing algorithm and simulated annealing. And apart from that, we also did the game search and the constraint satisfaction problem. A quick overview of the entire search. This is the uninformed type of search, where the performance measures. These performance measures are in terms of one, completeness, second, what is the time complexity, how much time does it take to complete the entire search. Third one is the space, how much memory does the search is going to occupy, and optimal, is it optimal with respect to some parameters. For breadth first search, uniform cost search, and iterative deepening and bidirectional, it is complete. Complete in the sense, if there is a goal, the search is definite to find the goal, that is the completeness. The time complexity, order of b power d for breadth first, and uniform cost search, it is almost the same. When c is equal to this epsilon, it is going to order of b power d, and a depth first, m is the maximum depth, and otherwise it is b power d, and depth limited, it is until that particular length limit we did the search. So, it would be when L is less than d, at that case order of b power L. And iterative deepening, it is b power d, and bidirectional search, because it is going to start from the start as well as the end, it will somewhere find in the middle, which is d by 2. The space complexity also, it is very similar, except for depth first search here and depth limited and iterative deepening, it is b m, it is just a multiplication, it is not exponential. The reason is only that part of the search, the depth of that can be stored into the memory. So, that is why it is very less compared to this the other point of view, which is breadth first search. And is it optimal for breadth first and uniform cost search, iterative deepening, and bidirectional, it is yes. and for these two cases it is not optimal, and sometimes if for infinite loops depth first will not be able to find the search path or the goal. And this is the summary of uninformed search techniques. And for uniform cost search, greedy and A star, we gave this type of formula where f of n is the evaluation function that consists of actual cost g of n, it is going to be the actual cost, and h of n, it is going to be the heuristic cost. For uniform cost search, we only consider g of n value there, and f of n in fact will be equal to g of n. For greedy best first, we assumed g of n to be 0, in which case f of n will be exactly equal to h of n. And for A star, we had both g of n plus h of n. And for hill climbing algorithm, if you remember, we did this type of the curve where this is an objective function x square minus of x squared plus 5 x plus 10, and this is the hill climbing path which has to climb. Suppose we start right here, the next random point is going to be here, and if suppose this point is A and B, if B is greater than A, then make this as a neighbor and move. So, that is how the immediate looking at the immediate neighbors, the hill climbing algorithm works until it reaches some point where it is non decreasing. It is, so it will keep on increasing. If there is a decreasing function, it will stop and say that yes, that is the goal. So, in for this example is very simple, because there is only one maximum, which is a global maximum, and this is the value that is being returned. And this is the optimal type of algorithm that we did, and there are other variations also which we have discussed in the earlier classes. And after that we did constraint satisfaction problem, and typically we did this map coloring problem of Australian map, where we said the variables are divided into x, di, x is going to be the variables and di are the domains, and the constraints are represented for this problem as no two adjacent regions are going to share the same color. So, this is one example of CSP. Now, in the last class I gave you two questions to work out on CSP. I will take a few minutes to discuss this question. So, here the question was define domain, variable and constraints for this problem. This is a typical university needs to schedule 3 classes, math, physics and chemistry in 3 available time slots 1, 2 and 3. The following conditions must be met. No 2 classes can be scheduled at the same time slot. Second, the physics class cannot be scheduled in slot 1. So, the question is, what are the, for CSP, we have to identify what are the variables which is going to be x, and what are the domains which is d, and constraints. And for this problem, the variables are going to be slot 1, slot 2 and slot 3, and the domain is going to be math, physics and chemistry. The constraints, there are 2 or 3 constraints that are given. No 2 classes, there are 2 constraints scheduled in the same time slot. So, if it is in slot 1, so each domain, each value from domain should be allotted only in one slot, that is the first constraint. And the second constraint is the physics class cannot be scheduled in slot 1. So, I can write slot 1 not equal to physics. So, this is one, and the other one we can represent in other terms like no 2 for slot 1 should be, if this is going to be D 1, D 2, D 3, the slot x should not be the same. If it is going to be x 1, x 2 and x 3, where this 3 represents that particular slot, a value from x should be allotted only to particular domain value. It should not, otherwise it is not going to obey this type of constraint. Okay. So, this is the answer for one of the answers for these two tasks, and you can have your own answers, but make sure that it obeys the constraint. Now, the second question that was given are given the variables x, y and z, and the domain values are x has 1 2 3, y as 2 3 and z as 1 3, and these are the constraint x not equal to y not equal to z and x greater than z. For this problem, we have to apply constraints propagation like AC3 algorithm. So, to begin, we have to draw this as a graph with 3 nodes x, y and z representing the variables here, and given these variables. So, x will take the value 1 2 3 and y takes the value 2 3 and z takes the value 1 3. The constraints are going to be represented as an edge. So, x not equal to y and y not equal to x, this is going to be one edge, and y x not equal to y and y not equal to x, this is a bidirectional arrow, and similarly y not equal to z, z not equal to y and x greater than z, z less than x. So, those two are represented using this arrow. This is y not equal to z, z not equal to y. Now, if you think about the AC3 algorithm, we will start with a queue with all the x y, y x, all the edges. We will have all the edges, and starting with one edge, delete an edge, update the other variables whichever is possible, wherever again the thing is y or whichever gets updated, whichever node gets updated, that incident node which is incident on it should be added back to the queue. You can refer back to the previous session of how we did AC3 algorithm for a problem. The same method you can use it in order to arrive at the answer. So, when this queue is becoming deleted one by one and getting updated, at one point queue will be null if there is a goal that is existing. If there is an assignment, proper assignment that is existing, then queue is equal to empty, and if it is not empty, it will again stop. So, if it is empty at this case, there is a proper assignment from domain to value of x. Otherwise, there is no assignment, it will again stop, it will be returned as a failure. So, this is the typical workout for CSP, and then we did adversarial search, the last type of search we did, where this is typically a two-player game, where one players win, one is winning means the other player is already losing. Otherwise, it is called as a zero sum game, where one person is having the maximum and the other person is having a minimum, or when we have maximum and minimum, it is going to be 0. So, this is a typical two-player game, and we saw a max min algorithm where one player wants to maximize it and the other player minimizing effect. And suppose we take this example, that maximizing and minimizing can be represented as a tree, where at the root, if it is going to be maximum of one player, the other player placed next, he wants to minimize it, and again the next player he wants to maximize it. So, it goes like this, and this is an example of an alpha beta pruning. This search is applicable when the entire tree need not be propagated. We can prune part of the tree, so that the space and time is intact, left intact, or which means the memory is not exploited further. Say if you take this example, You can see we did this in the last class, where this part of the tree is pruned, which means we need not go into this path in order to go further and evaluate. So, this is based on the alpha beta pruning. Coming to the performance of min-max and alpha beta pruning, min-max algorithm, it is very similar to that of breadth first search, where it is in the order of b power d and the space is b multiplied by d, very similar to that of BFS. For alpha beta algorithm, it is going to be order of b power d, this should be order of b power d, and the best this is a worst case. The best case is going to be square root of b. Why? Because the pruning is going to take place, and the space, it is the same as that of min-max algorithm. Now, having completed unit 2, which is the search technique, I am going into the next part of it, which is of AI, which is the reasoning process or the knowledge representation. This unit actually is sequentially, if we see, the first part was a little bit mathematical, where the search is the fundamental part of AI, and then comes logic. Logic is in the sense answering the question why, reasoning. Suppose if you say suppose the lights are switched off, we ask why is the light switched off? Because the person is not there, or there is no power. So, in that aspect of it, answering the question why, to find a proof in multiple ways, we use some techniques. And how do we do that? Mathematically or in programming sense or computationally. That part of it we are going to do in unit 3, which is the knowledge representation techniques, and here we will cover both the proposition logic and predicate logic. In unit 3, we will be covering first the knowledge representation outline, then we will see the logic terms, what are the definitions and terms that are available, and how is it and how can we understand it in simple terms. Then we will be going ahead with proposition logic, and whatever we did in discrete math, we will have a quick recap of all those. Then the theorem proving with natural deduction rules that will form the foundation for the forward chaining, and this is for the proof. Suppose again the question is, okay, why we are all doing this, why, and to answer the question why, and it should be a form of a proof, mathematical proof, or typically it can also be a proof in the natural language possible. So, first, what is knowledge representation? This one aspect of AI, it is to do with the representing of how we think, and that thinking can be represented in terms of knowledge. And there are two ways of doing it, one is reasoning, another one is learning, which I said at the first 2 sessions. Reasoning is answering the question why, and learning is through some means, we have some kind of experiential knowledge and through which that learning happens. So, typically what we know today available, which is outside in AI, they call it as machine learning, all those comes as a part of learning stuff. The other part is the reasoning is answering why, again it is through the logic side. Now, what is knowledge? Let us start with the basics of how to represent a knowledge. Now, in order to go into knowledge, we have to see what is data. When we say data in computer science term, it is usually associated with some kind of a database. And suppose you take this example, in the first column you see serial number, then roll number, the name of the student, the course and the marks. So, given this table, what will come to your mind? Okay, this student with roll number and serial number 23 has scored 95 in AI. Having this data, how do we say the information? What is information? Having some relationship association with that and semantic value, meaning that okay, since Ramanathan has got 95 marks in AI, that means he is doing good in AI. So, 95 it is close to 100, that is a maximum mark. So, we would infer that okay, he is good. Is there something else? Let us see this pyramid. Suppose you take the last column of it, which is here. This is data. the data is, we just have a bunch of strings and the values. We have read, this is 192.234.235. Some numbers and V 2. This is just a raw data. And then on the top of it, can we make some meanings to it? If we add some meaning to it, which means this red may indicate a traffic light that on the corner of a street. This is a type of bit, and George Street, that has turned red. That is the indication. And this 192, this indicates the position of GPS or the coordinates. This is the meaning of this data is information. Now, coming to knowledge, the context is the traffic light that I am driving towards has turned red. So, when we see this red data, this is the context with which it has to appear, and that we are going to call it as a knowledge. And then wisdom. So, when I see red, I better stop the car. So, this is the information that we have to achieve. So, this is easier with human, but how do we do the same thing with robots or any AI integrated system? Okay. So, we have to map it from data to information to knowledge to wisdom. Now, what are the general knowledge representation approaches? What are the general knowledge representation approaches? With relational database, let us say you take this table, this is the roll number as RN, we have the name Ram with age 11, height 4.8 and weight is 30, and second person is Greg with age 12, height 4.9 and weight 34. Now, the query with, suppose this is a database stored, this is a simple example, not typically a database, just for simplicity I have taken this example. Okay. So, from this table we ask who is heaviest. We can say that okay, this person with Greg is heaviest. Okay. But how do we do that with a relational database or at a higher level? How can we infer such knowledge or knowledge more than this? And that is, other type of knowledge is going to be some kind of inherited knowledge, something like the object oriented approach. Another type of knowledge is the inferential knowledge that comes from inference. Say for example, we have all men are mortal and Shakespeare is a man, and from these two statements we have to prove that Shakespeare is a mortal. Now, this is a type of inferential knowledge, because from given these two statements, nowhere it is said that Shakespeare is a mortal. So, we have to take Shakespeare here and mortal here. This is the inferential knowledge that is coming into play. And the other type of knowledge is the procedural knowledge. Procedural knowledge is a set of statements that has to be done for particular say for example, experiments. Experiments will have how to do certain things, that is the procedural knowledge, have with some basic facts on how to do it. Now, when we turn into logic, that is the inferential type of knowledge. So, now from all those type of knowledge we are just branching out to the inferential type, and for the inferential type of knowledge we are getting into the logic side. So, in the next few sessions we would be using only the logic side, and the first one is the proposition logic that deals with the simple propositions. Simple propositions are otherwise called as facts. The other part is the predicate logic, which is an extension to proposition logic. And the first question, why do we need logic for knowledge representation? Again, only with logic our inferential knowledge is possible. With the two examples that we saw, the Socrates example that we saw, where with the two statements we said that here these two statements, all men are mortal, Shakespeare is a man, and from these two statements we infer Shakespeare is a mortal. So, this type of inference is possible only through logic. Now, we will get into the first type, which is the proposition logic. And what is proposition? It is a simple fact. Example is today is sunny or today is rainy, that it is a fact. And suppose I say today is sunny or rainy, that also is a fact. Why? Because it can either be true or it can be false. I can represent a proposition that can be evaluated to true or false, that is a proposition. Another type of statements is interrogative. This is a question: what is the time now? When do we start? When is the class? All that are interrogative. Another type is the imperative statements or commands: take this pen, write down in your notebook. These are the imperative statements. Now, in this course we will be using only propositions, only facts. We will not be dealing with interrogative or imperative statements. Now, when we talk about proposition logic, again this is a quick recap of your discrete math, where it will start with syntax and semantics. Any logic will have the syntax and the semantic side. The language of proposition logic will have the basic atomic statements that will consist of P, Q, R. Like P can be something like it is sunny today, Q can be I have taken that umbrella, R can be something else, it is not sunny. The operators that we are going to do with proposition logic are negation, this is the first one, this is negation, this is and, this symbol stands for or, this stands for imply, and this is equivalent. And a language LP, we are going to define LP as a set of formulas that satisfies P, these P, Q and R, that belongs to the language of proposition. Q also is a belongs to language of proposition, R also belongs to language of proposition. Now, if phi is a language of proposition and psi is a language of proposition, then I write it is not phi or and, phi or psi, and phi implies psi, and phi equivalent psi, all those are also belonging to a language of proposition, and apart from that nothing else is LP. Now, how do we construct a formula based on this? Suppose I say, for example, A or B, this is a proposition. Suppose I write and A B, this is not a proposition formula, while this is a proposition formula. How do we know that this is a proposition formula and this is not a proposition formula? It is can be constructed through a tree, where if you see this example, this is a proposition formula, where we say not P or Q implies R, where this implies comes here, and this is the branching point, and this divides into two trees, and not P or Q comes here, and this R is the right of this tree, and this based on this symbol which is here, it again divides into not P and Q here, and this again splits into negation operator and P. So, this is how we construct the tree structure, and why we do this is to identify whether it is a well formed formula or not. This is called as WFF or well formed formula. Okay. So, in this session we have seen first a recap of search techniques from unit 2, and I started off with the knowledge representation. What is knowledge? The different types of knowledge, and then we went into the logic. I started off with the syntax of proposition logic, and in the next session I will be going into details of the formula of propositions and how do we use it for reasoning process.